Have you ever stopped to think about all the invisible connections that surround us? You've got Wi-Fi, Bluetooth, 5G, and they're all powered by this one piece of technology that's been around for over 100 years, but, it's still kind of a mystery for most of us. I'm talking about the antenna. And in this explainer, we're going to pull back that curtain and see what makes these things tick.
I mean, really think about it for a second. There are no wires, right? So how is your phone sending a signal all the way across town or even across the country? It feels a little bit like magic, but I promise you it's pure physics, and it all starts with the antenna.
So, here's how we're going to break it all down. First, we'll get into the fundamental spark, the magic of how an electric current literally becomes a wave. Then we'll see how engineers actually measure how good an antenna is. After that, we'll take a quick tour of some different antenna types. And finally, we'll see how this all comes together to power our connected world.
All right, so our first stop is the core concept. What is actually happening inside that little piece of metal that lets it just fling information through the air?
Okay, so at its most basic level, you can think of an antenna as a special kind of translator. It's a device that takes one form of energy and turns it into another. In this case, it takes a rapidly vibrating electric current and literally launches it into the air as these invisible electromagnetic waves.
So let's start with the simplest antenna imaginable, what a physicist would call a Hertzian dipole. Now, the math here is pretty deep, but the core idea, it's actually really simple. Just imagine electrons being pushed back and forth really, really fast along this tiny little wire. Well, all that constant acceleration creates these ripples in the electric and magnetic fields that are all around us. And these ripples, they detach and they travel outwards at the speed of light. That right there, that's a radio wave.
Okay, but here's a really key detail. Not all of the energy from that wiggling current actually escapes. Some of it just kind of forms this bubble of energy that stays stuck to the antenna. It's only the part of the energy that successfully breaks away and travels outwards that we call radiation.
And you know what's so cool? The physics equations themselves tell us this story. If you look at the math here, you'll see the magnetic field has two main parts. One part, the near field, has this 1 over r squared term. That means its strength just plummets with distance. That's the energy that stays close. But the other part, the far field, only has a 1 over r term. It fades way, way more slowly. And this is the piece that breaks free. This is the signal that can travel for miles. All right, so if we've got this energy escaping, how do we actually talk about how well an antenna is doing its job? Engineers need some real numbers, some solid metrics to compare one design to another. First up is something called radiation resistance. And yeah, I know, the word resistance usually sounds like a bad thing, right? Like something that just creates heat and wastes power, but not this time. In this case, it's actually a good thing. It's like a virtual resistance that tells you how much power is being successfully launched into space as radio waves. The higher it is, the better the antenna is at, well, radiating. Now, besides just being efficient, antennas can also be directional. And this little analogy really gets to the heart of the next big idea. A plain old light bulb just sends light out everywhere, but a laser pointer, it focuses all of its energy into one single tight beam. Antennas can do the exact same thing with radio waves. And that is precisely what directivity measures. It's basically asking how much more power is going in the best direction compared to a totally imaginary, perfect light bulb antenna. We call it an isotropic antenna that radiates equally in every single direction. So a higher directivity just means a more focused, more laser-like beam. So if we circle back to our super simple Hertzian dipole, the math shows it has a directivity of 1.5. What does that mean? It means it's already 1.5 times more focused in its strongest direction than that perfect sphere would be. It doesn't radiate in a ball, it radiates more like a donut. And this brings us to probably the single most important real-world number of them all, gain. Gain is actually really simple. It takes that focusing power, the directivity, and then it subtracts any real-world losses, like energy that's just lost as heat. It answers the one question that really matters. How good is this antenna, right now, at sending power where I actually want it to go? This is a number engineers really care about. So now that we've got these basic principles down, let's see how they actually build up into the physical antennas that we see all around us. Because it turns out there's a huge family of designs, and each one is tailored for a very specific job. A super common design is the half-wave dipole. As you can see here, its length is directly connected to the wavelength of the signal it's trying to catch. You've totally seen these before. They're the classic rabbit ears from old TVs. They're a really practical design, a lot more efficient and with a bit more gain than that tiny little theoretical dipole we started with. Now, check this out. This is where you see a huge jump in directivity. On the left, you've got our dipoles sending energy out in that broad donut shape. But on the right, that's a horn antenna. See how by flaring out the end, kind of like the bell of a trumpet, it physically guides the energy? It shapes it from a broad wave into a much more focused beam. And to get an even tighter beam, you can take it one step further. You use that horn antenna as a feed, and you point it at a parabolic reflector. Yep, a satellite dish. The magic here is all in the shape. That precise curve makes sure that any wave leaving the horn gets reflected outwards in a perfectly parallel, super concentrated beam. This is exactly how we get enough gain to talk to satellites that are hundreds or even thousands of miles away.
Okay, so we've gone from a simple piece of wire to a giant satellite dish. Let's bring this all back home and see how these exact same ideas are working inside the technology we use every single day.
So where are the antennas in your phone? They obviously don't look like rabbit ears. Nope, they look like this. This is a microstrip or a patch antenna. It's basically just a very carefully shaped piece of metal over a ground plane, etched right onto a circuit board. This incredible miniaturization is the whole key. It's what lets us pack dozens of different antennas for Wi-Fi, for Bluetooth, and for 5G, all inside your tiny smartphone. And designing one of these things, even though the math can get pretty hairy, follows a really logical process. First, an engineer picks the frequency they need, like for a Wi-Fi signal. Then they use these very specific formulas to figure out the exact size of that little metal patch. And those dimensions are everything. They have to be perfectly tuned to the wavelength of the signal they're trying to send or receive.
Now, here's a just beautiful and incredibly powerful principle in physics. It's called reciprocity, and all it means is that every single property we've talked about, gain, directivity, all of it, is exactly the same whether an antenna is transmitting or receiving. This is what lets that single antenna in your phone both send your voice out and receive the other person's. It's a perfect two-way street.
And it all comes together in this one beautiful formula, the Friis transmission equation. This is like the master recipe. Just look at the pieces we've talked about. Here's the power of the transmitter. Here are the gains of both the transmitting and the receiving antennas. That's our focusing power. And all of that is balanced against the distance the signal has to travel. This one equation lets an engineer calculate with amazing accuracy if a signal is going to be strong enough to be heard. Our entire journey, from a wiggling electron to a signal at your phone, is basically summarized right here.
When you really stop and think about it, the scale is just staggering. It all starts with a tiny, wiggling electric current, which then gets shaped and focused by some clever geometry into a beam that carries our world's information across cities, oceans, and even across the solar system. It's just a perfect example of how understanding one fundamental law of physics lets us completely reshape our reality. It really makes you wonder, what's the next invisible force that we're going to learn how to speak?